What we'd like to do is talk about the gradient vector geometrically. We know how to find it, and we just take the partial derivatives and compile them to make a vector. What we would like to know is, hey, what direction does it point and how long is it? And all that actually comes from our definition of directional derivative, at least our formula for directional derivative. We know that our formula for directional derivative, and we call that FU, right, is just equal to the gradient dotted with a unit vector in the direction of the chop. Now what we're going to do is say, hey, what's the definition of dot product? Well, the definition of dot product is the length of the first vector times the length of the second vector, but use a unit vector, so its length is 1, times the cosine of the angle between them. Now we can get a couple conclusions from this already. Yes, the size of the directional derivative in any direction is going to be less than the size of the gradient vector, because cosine is always less than 1. Now secondly, the only time the chop in a direction can actually be as big as it possibly can be is if it would be actually the slope, would actually be the length of the gradient vector in that direction. So the biggest the slope can ever be when you're standing at a point on a surface is the length of the gradient vector. Now, when can it actually be that? Well, the slope can only be as big as it possibly can be when what? When the cosine of the angle between the gradient vector and the direction of the chop is 1. Let's write that a different way. So the slope of a chop can only be as big as possibly can be when the angle formed by the gradient vector and the direction of the chop is 0, right? This says, because this only happens when the gradient vector is parallel to the direction of the chop. In other words, the slope can only be as big as it possibly can be, and that's the length of the gradient vector, when we chop in the direction of the gradient vector. We chop in the direction of the gradient vector. So let's say this much, right? The gradient vector, points in the direction of greatest increase. Or fastest increase, however you want to phrase it. We'll look at a contour diagram in just a second, but we'd also like to know how long the gradient vector is. So let's take away some of the stuff at the top. And what we're going to do is we're going to say, what is the slope in the direction of greatest increase? What is the slope in the direction of greatest increase? Well, first off, we know that slope is equal to the length of the gradient vector. We have that over here. Let's see here. We go like this. And we can actually just do this with a little calculation if we had to, right? Because this is just going to be the gradient vector dot a unit vector in the direction we're going, right? And that should just be, let's see here. I want to dot it with a unit vector in the direction of the gradient vector. So we're going to get a unit vector in the direction of the gradient vector. And this is just going to confirm what we already have, like that, right? Remembering that when we dot a vector with itself, we get the length squared. And one of the lengths cancels, and we get what we thought we were going to get. Let's see here, what are we going to get? We're going to get that the length of the gradient vector is the slope in the direction of greatest increase. And those actually give us the two things we want. They give us the direction of the gradient vector points in the direction of greatest increase, and the length of the gradient vector is equal to the slope in that direction. A real quick example, then we'll try to do something with a real contour diagram instead of a pretend contour diagram. But meanwhile, let's just have a pretend contour diagram just here for a second. So I'm just going to go like this and say this is x and this is y. And we'll go 1, 2, 3, 4, and try to be consistent. And here, and here, and here. And let's just have some contours that just run along the way. Let's go like this. Now when we're finding slopes, we like to zoom in until it looks linear anyways. Let's just put some z values on here. How about z equals 5, z equals 10, z equals 15, z equals 20, z equals 25. And I'm looking at a point, and I want to say, what's the direction of the gradient vector? Well, I know how I can make the slope decrease. I can do that by pointing in direction of decreasing z. I know how I can make the z values not change at all, just point in the direction of the contour. If I want to point in the direction of greatest increase, I need to get off that contour as quickly as possible and point in the direction of increasing z, right? So what you're going to see there, in order to do that, I have to get off the contour as quickly as possible. So we're going to see that the gradient vector is going to be perpendicular to the contour, pointing in the direction of greatest increase. If I want to know the length, right, the length of the gradient vector, it's supposed to be the slope in that direction, right? Well, that should just be delta z over the length of the run. The delta z in this case, right, is 5. The length of the run is just about this much, and if I take this much and walk it over here, it looks about that long, which looks about, I don't know, 0.7. Just a reminder of what we're doing, right? We're going from one point to the next. The length of the gradient is the slope in that direction. Delta z is 5. You can see the contour is going up by 5. The length of the run, I just literally measured. We get something like 5 over 0.7, which is 7.1-ish, I guess. So that's about how long the gradient vector would be. Now, by the way, that says that the little tiny gradient vector I drew here is way too short, right? Because one goes this way, one goes this way. It should be going length 7 way probably off my board. It's got to be length 7. So in this case, the gradient vector is much longer than what I can actually draw. All right, we're going to go over to a different contour diagram now, one from a function instead of one I just sketch, and we'll see if we can't do the same sort of thing there. Just draw the gradient vector, just think about drawing the gradient vector and find its length.